All right, today we're going to dive into one of the most elegant ideas in all of computer science, persistent data structures. Seriously, it's like giving your data its very own built-in version control system. I mean, just think about that for a second. What if your data structure had built-in time travel? Imagine every single change you ever made was reversible, and every previous version of your data was just there, instantly accessible. Sounds kind of like magic, right? Well, it's not magic. That is the core promise of persistent data structures. The whole idea boils down to one word: immutability. You see, you never actually destroy or overwrite data. Instead, every single update operation creates a brand new independent version of the structure, while perfectly preserving all the old ones. They're all still there, ready to be used at a moment's notice. And, this idea isn't some new fad. This quote takes us all the way back to the formal definition from 1989. The folks who pioneered this stuff defined it with this beautiful simplicity. It's a really simple premise, but with incredibly powerful consequences. But hang on, if you're creating a whole new version every single time you make a change, doesn't that just eat up a ton of memory and time? That is the million-dollar question. And the answer lies in one very, very clever trick. The core idea is sharing. Just look at the difference here. With a standard, or what we call a mutable update, you change the data right where it is. And poof, the original state is gone. It's lost forever. But with a persistent update, a new version is born, leaving the original completely untouched and ready to go. You really do get to have your cake and eat it too. And this is the secret sauce that makes it all so efficient. The technique is called structural sharing. Instead of wastefully copying the entire thing, new versions just reuse the vast majority of the old structure's parts, the nodes that didn't change at all. It's brilliant. And this isn't a one-size-fits-all kind of deal. There are actually levels to this. With partial persistence, you can look at any old version, but you can only change the very latest one. Then you've got full persistence, which is even wilder. You can go back in time, change any past version, and create a whole new branch in your data's history. And finally, confluent persistence even lets you merge those different timelines back together. How cool is that? Okay, so we've got the what and the why. Now let's get our hands dirty with the how. We're going to look at the most common technique for making this happen, especially in tree structures. It's called path copying. All right, let's walk through a quick example. So we've got our original tree, let's call it version A. To add a new element, we first figure out the path from the very top, the root, down to where the change needs to happen. Then, and this is the absolute key, we create new copies of the nodes for only that specific path. That's it. Finally, we link up these new nodes. And here's the magic. All the other branches and subtrees that weren't touched, we just point to them, we share them. And just like that, we have a new root for version B, which lives right alongside the original version A. And that right there is why this is so incredibly efficient. You only copy the path. In a big, balanced tree, that path's length is tiny compared to the total size. You're not copying a million nodes, you're copying maybe a handful. Okay, this all sounds fantastic in theory, but what do the numbers actually look like? Let's get real for a second and talk about performance and, of course, the trade-offs. This table just lays it all out perfectly. Now, that O notation, that's big O, and don't let it scare you. It's just a simple way to talk about how an operation's cost grows as your data grows. So a normal, mutable update is O of 1. It's crazy fast, but you lose your history. Making a full copy is O of n, which is just brutal. It gets slower and slower the bigger your data gets. But path copying, it hits that sweet spot. O of log n. That means its cost grows incredibly slowly, even for gigantic data sets. It's fast, it's efficient, and you get to keep your history. And to really drive this point home, just look at this chart. For a structure with 1 million items, a full copy means you're creating 1 million new items. With path copying, you're looking at maybe 20. That isn't a small improvement, it's a total game changer. Okay, one quick but really important clarification, because this trips people up all the time. When we're talking about data structure persistence, we mean this version-preserving kind, keeping history in memory. We are not talking about persistence like in databases, which means saving data to a disk. They're two totally different ideas that just happen to share the same name. So this is all really cool theory, but where do you actually use this stuff? Where does this powerful idea show up in the software you use every single day? Let's talk about its real-world superpowers. Believe me, this is not just some academic toy.
Because the data is immutable, it literally never changes. You can safely share it across multiple threads at the same time without needing complex, slow locks. That's a massive win for performance. And that undo/redo button in your favorite app? Yep, it's just stepping back and forth between these preserved versions, all made super efficient by that structural sharing we talked about. It's also the default way of doing things in functional programming, and it's a core idea behind a lot of modern databases.
So if you're ever in a technical interview and this topic comes up, this is the one thing you need to remember: O log n. That's the typical time and space cost to update a balanced, persistent tree. It's the magic number that makes this entire concept not just possible, but powerful. So there you have it. We've seen how immutability and clever structural sharing can basically give our data time travel, making really complex problems so much simpler and safer to solve. The only question left is, when could time-traveling data solve your next problem?